Welcome to this video. Before we discuss anything in this video, what is this video about? So this video is about applying the basic concept of saturated liquid vapor mixture to find out the specific volume of saturated liquid vapor mixture. I have already discussed the basic concept of saturated liquid vapor mixture in my previous two videos. Links are in the description. So second thing we are going to learn in this video is, if I give you a specific volume, how to identify if the given volume corresponds to saturated liquid vapor mixture or not. So what is that condition which decides if this volume corresponds to saturated liquid vapor mixture or not? That we are going to see. The third thing, we are going to use steam tables to find out the specific volumes, saturation temperature of the mixture. So the second thing is, why is this important to study? So from this video, you will apply your theoretical concepts to solve the real life numerical problem. So you are testing your theory knowledge to solve numerical problem. So step by step we are going to solve this numerical problem. The first thing we are going to do is to decide, when a specific volume is given to you, what condition defines that volume corresponds to saturated liquid vapor mixture. Then we are going to calculate what is the saturation temperature of this liquid vapor mixture. Then we are going to calculate the dryness fraction of the mixture. Lastly, we are going to calculate what is the volume of vapor in this mixture. So here we have 80 liters of vessel which contains 4 kg of refrigerant, which is at 160 kilopascal. For this refrigerant, determine temperature, dryness fraction, and how much volume is occupied by the vapor phase. So let us answer this question before we solve this numerical. Is this given refrigerant is a saturated liquid vapor mixture or not? So let us discuss how can we identify saturated liquid vapor mixture using specific volume. This TV diagram, I have already explained this TV diagram in my previous video. I will give you the link of that video in description. So on this TV diagram, the condition 2 represents saturated liquid condition, condition 3 represents saturated vapor condition, and condition 5 represents saturated liquid vapor mixture condition. We can see here condition 5 is in between condition 2 and condition 3. From x-axis, the specific volume of condition 5 is in between specific volume of condition 2 and specific volume of condition 3. We can also say that specific volume of condition 5 is greater than specific volume of condition 2, but it is less than the specific volume of condition 3. What is specific volume of condition 2? It is Vf because it is a saturated liquid. What is specific volume of condition 3? It is Vg because it is a saturated vapor. Specific volume of condition 5, it is a mixture condition. So let's say it is specific volume of given mixture. So I can say specific volume of given mixture is greater than Vf, but it is less than Vg. So at a given pressure or temperature, if the given specific volume to you is greater than Vf and it is less than Vg, if this condition is satisfied, that condition represents saturated liquid vapor mixture condition. So now at a given pressure of 160 kilopascal, I will calculate what is the given specific volume of refrigerant, and I will compare that specific volume with Vf and Vg. Vf and Vg we can find out from steam table at 160 kilopascal. So we have given mass of refrigerant 4 kg, pressure 160 kilopascal, given volume is 80 liters, which is 0.08 meter cube. How to calculate specific volume of refrigerant? Given refrigerant, volume of refrigerant is equal to mass of refrigerant multiplied by the specific volume of the refrigerant. So the specific volume of refrigerant is equal to volume of refrigerant divided by the mass of refrigerant. Volume of refrigerant is 0.08 meter cube, mass of refrigerant is 4 kg. So the specific volume of given refrigerant is equal to 0.02 meter cube per kg. So now we have specific volume of given refrigerant. Let us check the Vf and Vg values from steam table at 160 kilopascal. So here we have steam table for refrigerant R-134a, which is a pressure table because pressure is given to us. And here we have specific volume given in meter cube per kg. Specific volume of saturated liquid, here we have Vf. Specific volume of saturated vapor, we have Vg here. And here is the pressure table. So pressure in kilopascal given to us, and the corresponding saturation temperature is given here. So the pressure for our refrigerant is 160 kilopascal. So the corresponding Vf is equal to 0.0007435. Corresponding Vg is equal to 0.12355. So from steam table at pressure 160 kilopascal, Vf is equal to 0.0007435 meter cube per kg. Vg is equal to 0.1235 meter cube per kg. So clearly the given specific volume of refrigerant, which is 0.02 meter cube per kg, is greater than Vf and it is less than Vg. So this satisfied the condition of saturated liquid vapor mixture. So this condition is satisfied and we can say that yes, this is a saturated liquid vapor mixture condition. So now we have identified that this refrigerant is a saturated liquid vapor mixture. Let us calculate the temperature of this mixture, dryness fraction, and what is the volume of the vapor in this mixture. So let's find out the temperature of this refrigerant, which is a saturated liquid vapor mixture. Saturated liquid vapor mixture exists in phase change region. So this point phi is in phase change region where pressure is equal to saturation pressure and temperature is equal to saturation temperature. So if we go to property table of R-134a refrigerant, we can check for a given 160 kilopascal what is a saturation temperature. That saturation temperature is the temperature of our refrigerant. So from the property table for refrigerant R-134a, the pressure is given and the corresponding saturation temperature is given here. So at 160 kilopascal, the corresponding saturation temperature is equal to minus 15.6 degrees Celsius. So from property table of R-134a refrigerant, at a given pressure of 160 kilopascal, the saturation temperature is minus 15.6 degrees Celsius. As this refrigerant is a saturated liquid vapor mixture, its temperature is equal to saturation temperature. So at a given pressure of 160 kilopascal, the temperature of refrigerant is equal to minus 15.6 degrees Celsius. So now I want to calculate dryness fraction of this liquid vapor mixture refrigerant. For dryness fraction and specific volume of liquid vapor mixture, I have two videos. The links are given in the description. So for dryness fraction, I can use this equation x is equal to mg by m total, but mass of vapor is unknown and dryness fraction is unknown. So there are two unknown, so we cannot use this equation. So the second equation is the specific volume of liquid vapor mixture is equal to Vf plus x Vfg. So in this equation, the specific volume of liquid vapor mixture refrigerant is given to us already. We have calculated that. That is 0.02 meter cube per kg is the specific volume of refrigerant mixture. Vf, we know that at pressure 160 kilopascal, Vf is given to us. Vfg is Vg minus Vf. So we know that Vg is given and Vf is given. We can calculate Vfg. The only unknown is dryness fraction. So we will use this equation. So the specific volume of mixture is equal to Vf plus x Vfg. We can take this Vf on left hand side. V mixture minus Vf is equal to x multiplied by Vfg. Vfg can be written as Vg minus Vf. So on right hand side, x multiplied by Vg minus Vf. I can write x is equal to V mixture minus Vf divided by Vg minus Vf. We can put the values of specific volumes. V mixture is 0.02, Vf we know that 0.00073435, Vg is 0.1235 minus again Vf. All these values are given at this particular pressure. So the dryness fraction is equal to 0.157. So the last part of this numerical problem is to find out the volume of vapor in this saturated liquid vapor mixture refrigerant. So the volume of vapor is equal to mass of vapor multiplied by the specific volume of vapor. So the specific volume of vapor Vg is already known to us. So the problem here is we don't know the mass of vapor and we don't know the capital Vg. So if we can find out what is the mass of vapor, we can find out capital Vg, which is the volume of vapor. So mass of vapor we can find out from dryness fraction. So dryness fraction is mass of vapor divided by the total mass of refrigerant, which is already given to us 4 kg. And we know that dryness fraction is 0.157. So I will write here dryness fraction is equal to mass of vapor divided by total mass of refrigerant. I can write mg is equal to x multiplied by the total mass. Dryness fraction is 0.157 multiplied by the total mass of refrigerant is 4 kg. 4 kg. So the mass of vapor mg is equal to 0.628 kg. That is mg. So the volume of vapor in this refrigerant is equal to capital Vg is equal to mg multiplied by this specific volume Vg. Mg is 0.628 kg multiplied by the specific volume Vg at 160 kilopascal is 0.1235 meter cube per kg. This kg will get cancelled. We will get capital Vg is equal to 0.0776 meter cube. So this is the volume of vapor in this refrigerant. So the volume of vapor refrigerant is 77.6 liters. The total volume of refrigerant is 80 liters. That means we have 2.4 liters of liquid refrigerant.